topic is improper integrals. Now, an improper integral is an integral where one of two things is true. Either the interval of integration is unbounded, or two, that's possibility one, and possibility two is the integral is unbounded on the interval of integration, which is a different situation. What that looks like really is like this. So in the first instance, what we have is an interval of integration that's unbounded. In other words, instead of just being, let's say, a finite interval of integration that goes from say a up to b like that, the interval extends from a all the way out to infinity. So here what we're doing is we'd be integrating, let's say, the integral from a to infinity of f of x dx. Now, in the other case, the one you see on the right, we have an ordinary finite of integration, interval of integration that runs from, let's say, 0 to a. So we're integrating from 0 to a function f of x. It doesn't look like anything is amiss here, but if you look at what the function actually does, you see that it's not even defined at 0. It actually tends toward infinity on the interval of integration. So the thing about improper integrals is that somewhere on the interval of integration, they have some sort of an infinity problem that makes them different from regular integrals. This, on the left, the situation that we have is what we generally call a type 1 improper integral, and on the right, it's a type 2 improper integral. Type 1 integrals are going to be the more important type of integral in this course, but we're certainly going to start, we're going to study type 2 integrals a bit in this section. Now, the interesting thing is, you might look at these and say, well, what does it even mean to integrate on an infinite interval? After all, isn't it true that the yellow area must be infinite? It certainly looks like that's just obvious that we're talking about a region that has an infinite width. How could it have anything but an infinite area? This is the surprising thing. It turns out that for functions that look like what I've drawn here, y equals f of x, for functions with that shape, it turns out that sometimes the area under the curve is infinite and sometimes it's finite. And the only way to know is to actually go through the calculation. Well, actually, I should say there are a couple of rules that allow us to determine it once we've done the initial calculation. But the point is that there's a very well-defined way to understand whether this is going to come out to a finite number or an infinite number. And that's why we study improper integrals. So, oh, and by the way, the same thing for type 2. It looks like here we have a region of infinite height, so certainly it must be infinite, but for the same reason, sometimes it's finite and sometimes it's infinite. So let's define how we talk about improper integrals. So let's suppose that f is continuous on the interval ab for all numbers b greater than a. So in other words, all we're saying is that regardless of what we choose for a and b, this integral from a to b of f of x exists and it's well defined as a number. So then what we're going to do is we're going to define the integral from a to infinity of f of x as the limit as b approaches infinity of the integral from a to b of f of x dx. I want to stop here for a minute and explain why we need a definition. Integrals are defined on a finite interval. When I talk about a definite integral from a to b of f of x dx, this is a definite integral. This is what the integral that you know about and that you know how to calculate through the fundamental theorem of calculus. The assumption is that I have a finite interval ab. So I need a new definition in order to be able to put infinity as a limit of integration. And what we're doing is we're defining that in terms of the integral from a to b as b becomes infinite. So just going back to this drawing, what I'm doing is I'm supposing that I put here the number b, and I just keep moving it further and further to the right until it gets out to infinity. That's what I'm doing when I say that I'm taking the limit as b approaches infinity of the integral from a to b of f of x dx. A doesn't move, but b keeps moving to the right. So similarly, we can do this on the other side. If I were to draw a picture of that, I'd say suppose that I have something like that function where now I've got, that's b, and now I've got a moving out to negative infinity. So it's really the same thing. I can define the integral from negative infinity up to b of f of x as the limit as a approaches negative infinity of from a to b of f of x dx. In other words, same picture as we drew here, but we're letting the infinite part go to the left instead of to the right. And then finally, if f of x is continuous on all real numbers from negative infinity to positive infinity, then we can define the integral from negative infinity to positive infinity of f of x as the integral from negative infinity up to c plus the integral from c up to infinity. You've probably seen a situation like this, especially if you've taken a stat course. That's the bell curve, or the what you probably learned is the cumulative distribution function, or sorry, the density function of the standard normal random variable. And what you learned is that the area under this curve, it sums up to 1. And what that's saying is that here we have a situation with the integral from negative infinity to positive infinity of that particular density function is equal to 1. If you don't know what density functions are, or you don't know about statistics works, don't worry about that. The point is, this is an example of a function that's actually defined from negative infinity to positive infinity, and we have to actually define the area under that curve as an improper integral. We'll get to that. So that's what this picture means. And the point is that I can break this up any place at C. I don't have to, there's no reason I have to choose, let's say, the middle value of 0. I can just pick any number C and integrate from negative infinity up to C, and then in a different color go on from C to positive infinity. It doesn't matter where I break it up at C. C can be put any place, and you get the same answer either way. So this is the definition of the improper integral. So what we would do is we'd say that an integral from a to infinity of f of x dx is an improper integral. And so are the other ones as well. It's just that, and what I'm describing here is how we define that in terms of a limit. Now, since improper integrals are defined as a type of limit, like any other type of limit, they can either exist or not exist. If the limit does exist, we say that the improper integral converges, and if it does not exist, we say that the improper integral diverges. That's the language that we use for the situations where the integral either, where the limit that we use to define the integral either exists or doesn't exist.